In this section, I'm going to talk about the design of the cross section. What does it mean, design? Design means to determine the section, dimension of the section. Okay, that is design. Again, design is to determine the section and dimension of the section. In this case, we use plastic design concept. Okay, plastic design. We use plastic design. Now, please consider a beam. It is fixed end beam under concentrated load at the middle. The beam has a length of 10 feet. Okay, under the gravity load Q equal to 1 for 1 kip. Okay, this is gravity load. And because we use plastic design, then we assume 3 plastic hinges occur. Okay, so we have a moment diagram corresponding to 3 plastic hinge. So here MP, MP, and MP. Then the total is 2 MP, and you know that the total from here to here is QPL over 4. And in plastic design, we use this equation. Okay, so lambda is load factor for this and live load. Lambda equal to 1.7. It is load factor. Then that's why here we have load factor 1.7 multiplied by the load, gravity load, equal to 240 kip. So the plastic load is 240 kip. Okay, this is plastic load requirement. Then we are going to calculate the section to satisfy this load. What is the section? Okay, what is section? Okay, now we have MP equal to QPL over A from here. Then we have QP, we have L and A. Then we have MP equal to 300 kip feet. Okay. And now we can calculate the plastic section modulus. Okay, you have MP equal to what? MP equal to plastic section modulus multiplied by sigma y. And you have sigma y. We assume it is steel. So sigma y equal to 36. So determine section mean determine plastic section modulus. Okay, so here we have Gx equal to MP over divided by sigma y and equal to this 100 inch. So here we have 12. What is 12? 12 means the transforming factor from because it is feet, and we should use inch. Then it is transform factor. Then finally we have G, the requirement, equal to 100. And this is requirement for this section. Then how to determine the section? For example, we assume to use the I section. Then you can use the design code manual. For example, here we use AISC. Then we can check and select some different section. For example, we have 4 different sections here and the corresponding CX. Okay, then which one should be selected? This one. So for all 4 are meet the requirement, but this section is better because it's lighter and more resistant than compared to the first and the second, and lighter. So finally we use this section. Okay, and that is a design using plastic design concept for the beam. The next problem is analysis of the section. The previous one is design and this one is analysis. What does analysis mean? Analysis means calculate the load. Okay, what is load? So section is a given. How to determine the load? That is analysis problem. Again, we consider the same beam with the length of 10 feet and the concentrated load at the middle, QP, and we have to calculate QP. And we should have a section, and this is a section. It is a little bit complicated section, the I section, and this one is called striplet. Here, striplet has the width of 8 inch and the thickness of 0.75 inch. Then to determine QP, then this is I section. Okay, I section. So with this section we have G equal to 110 and we use A36 still, mean it is sigma y equal to 36. Actually we have QP equal to 8 ampere over L for this beam. Okay, so QP is a function of MP. So for analysis, to determine QP, it means we have to determine MP. So problem now is how to determine MP. And I already introduced how to determine MP. So for determine MP, we have to calculate this section. So here is P and A, and it is A1 in the compression, and this part is A2 in tension, and A1 should be equal to A2. Then we can calculate, we can determine P and A, and let's say the distance between P and A and the center line of the original section is Y. And to determine P and A, we have to determine Y. And how to determine? I'll show you. This is a stretch diagram of the whole section. And for convenience of calculation, we can divide into 2 parts. The first part is for the original section. Okay, and this one is for only considering the striplet. Okay, here we go. First, we have to calculate A prime. A prime in the area, small area here. This area should be equal to the area of the steel plate here divided by 2. Why? Because to make the section divided by 2 parts, A1 equal to A2. Okay, so we can calculate A prime equal to 8 multiplied by 0.75 divided by 2 equal to 3 inches square. So from here we have y equal to this area divided by the thickness here of the web. So now we have y equal to 7.89 inches. And now we have y. Of course, we have p and a and y. Then now very easy to calculate d prime or f prime something. Then now we calculate MPO. MPO is for the original section. MPO equal to g multiplied by sigma y, and g of the section already given. Then MPO equal to h. MPC equal to f prime multiplied by d prime. Here's f prime and d prime. What is f prime? F prime equal to 72 multiplied by 3. Here's 3. Okay. Here's 3. And multiply by 72 here equal to this one. And d prime, what is d prime? D prime equal to this one. Here 20.82 divided by 2 plus 0.75 divided by 2 minus 77.89 divided by 2, then finally equal to this one, that is d. Then we have PC equal to this. And now we have MP equal to this part plus this part. And finally we have MP equal to this. Then because we have MP, then now we have QP equal to this one. That is final solution. Next, this section, we are going to consider the effect of axial force on MP. Okay, the effect of axial force on MP. In general, let's consider an arbitrary section, a beam with arbitrary section like this. So we are going to see the structure behavior of the section with different level of the moment. So axial force without moment bending moment, then we have stress diagrams like this. If the moment is applied with small value of the bending moment, then the stress diagram will be changed like this. If the moment is increased, what happens? Moment is increased, then the initial ending or the elastic limit will be occur and sigma y. Okay, then it keep increasing the bending moment, then we have elastic, plastic. It is plastic sigma y, and this part is elastic, and keep increasing the bending moment, then we have fully plastic like this. And now we are going to see how the action force affect on the MP. For rectangular section, under both bending moment and action force, then the stress diagram will be like this. not in the middle but here. So here is P and A. It depends on the value of the action force. It can be divided into two parts for convenience of calculation. Okay, can be divided into two parts. The first part is for P, due to P. Okay, due to P, mean due to action force, and the second part is due to MPC, moment. By using this diagram, then we can calculate P equal to 2 sigma y here, sorry, 2y0 multiplied by sigma y. It is P. Then from that, we can calculate y0 equal to P divided by this one. And what is MPC? MPC equal to sigma y multiplied by this one, then multiplied by the width of the beam B, and multiply by the level M, and equal to this one. The MPC equal to this one. And we already have MP equal to this. Sorry, PY equal to this. And MP equal to this. We already know. Then now we have the ratio between MPC over MP. MPC over MP. MPC is here, divided by MP is here. Then we can calculate MPC over MP equal to this one. So this is the ratio between MPC over MP. This should be smaller than or equal to 1. Equal to 1, right? Smaller than or equal to 1. Y flange section. This is Y flange section. In Y flange section, we have two parts. This is flange. Okay, so for flange, we have a flange, a section of flange, and AW means a section of web. Okay, section of web. First of all, we have to calculate to determine where is P and A. Okay, because it's depending on the P and A, and the P and A depending on the section. And first of all, we assume it is special case. In special case, the P and A is located here on the upper surface of the bottom flange. Okay, so we call it special case. For special case, we can divide into two parts, PB and MB. PB is only for the load is in the wave. Yes, and the moment is only for the flange. So we have MP equal to A multiplied by sigma y. It is my of the whole section. PB is only this one, equal to this one. Very simple, right? Sigma y multiplied by it is A W. And MB equal to sigma y multiplied by AF multiplied by DF. Here's DF, here's AF. And we have ratio between PB over PY. PB over PY equal to this one. Then forward. Now P and A in web. P and A in web here. What does it mean? Mean P over PY. P is action force over PY. Py is here. If P over Py greater than 0 and smaller than this ratio, Pb over Py, then PBC, MPC over MP equal to this equation in textbook. So please check in textbook, okay? Equation 257. If P and A in flange, when P over Py smaller than 1 and greater than this ratio, then MPC over MP equal to this equation. Please check in the textbook this equation, okay? For practical design, in practical design, so here for web flange design, web flange section with different ratio between AF and AW. If the ratio equal to 2, then this curve. If this ratio equal to 0.5, then this curve. If the ratio equal to 0 mean rectangular section, then we have this curve. But it is very complicated. So for practical design, we can use this curve. That is of approximation curve. Okay, it is used for practical design. So if we can divide into two parts, this part and this part. If this ratio is smaller than 0.15, then we can use MPC equal to MP. Okay, equal. And if P over Py greater than 0.15, then we use this equation. Oh, sorry, this equation. Okay, this equation. So again, in practical design, for rectangular section and I section, okay, rectangular section and I section, we use the same equation for rectangular and I section. If the ratio between P over Py is smaller than 0.15, then MPC is assumed to be equal to MP. Okay, it's assumed to be equal to MP. But if the ratio between MP divided by MY greater than 0.15, and of course it should be smaller than 1, then this curve, this linear relationship is used. And it means that is this equation. MPC is a function of P over Py and MP. And MP here is some elastic moment you can calculate depending on the section. And P is load, apply load, okay, apply load. And Py is Py is ending strength of the section, ending strength of the section. Okay, so now from now on, you can use this equation for practical design of I section or rectangular section.